Hello and welcome to another lesson on A-level physics. Today's learning intention is to be able to solve problems using equilibrium rules. The success criteria for today is to be able to explain equilibrium in terms of a closed triangle of forces and to be able to solve moments problems when forces are not at 90-degree angles to the lever. So let's start off by considering equilibrium of forces once again then. We've got on the board a diagram that shows an object being acted on by three forces. Now the condition for that object to be in equilibrium is if the resultant force is zero. Now being zero, the resultant force means that when those three forces are vector added together, that comes out as zero. So in other words, F1 plus F2 plus F3 is equal to zero. Now to do the vector addition of forces, remember we need to draw the arrows for the vectors tip to tail. So if I draw F1 in the same length and at the same direction that it's going on, there's F1. Now when I'm adding F2 to F1, I would need to draw it so that the tip of F1 is at the tail of F2 as shown here. And then finally I can draw in F3. Again, I will start it from the tip of F2 and there it goes. Now you can see that those three forces have made a closed triangle. There's no break in it, it is a complete loop, and so therefore we can say that this object is in equilibrium because the forces make a closed vector triangle. Now the second success criteria for today was to consider moments problems when the forces are not perpendicular to the lever, which is what we're going to look at here. This is quite a worded example, but if we read through it together, then we can have a go at solving it. It says a public house sign is fixed to a vertical wall as shown in the diagram. A uniform metal bar 0.75 metres long is fixed to the wall by a hinged joint. The wire is fixed to the wall directly above the hinge and to the free end of the horizontal metal bar. The wire makes an angle of 40 degrees with the wall. It then says a single support holds the sign and is mounted at the midpoint of the metal bar so that the weight of the sign acts through that point. The combined mass of the metal bar and the sign is 12 kilograms and the mass of the wire is negligible. By taking moments about the hinge end of the bar or otherwise, calculate the tension in the wire. So this actually is a moments problem. That metal bar is going to be behaving as the lever. And then of course there are two forces acting on it. We've got the weight of the sign and the bar itself acting from the centre of the metal bar, and then acting from the end furthest from the hinge we've got the tension in the wire. Now I can draw out those forces as shown there. We've got the weight acting down from the centre and the tension acting at the far end from the hinge. The issue with that tension force though is that it is not at 90 degrees to the lever, and we will need to resolve that tension force to get the component that is at 90 degrees to it to see what size force is actually going to be causing an anti-clockwise moment. I'm going to label on that diagram the different distances that we have. So I know that the whole metal bar is 0.75 metres long, and so halving that I can say that the weight is 0.375 metres from the hinge. Now I can also work out the angle that the tension makes to the metal bar, because as you can see the wire is actually making a right angle triangle with the metal bar and the wall. Now we've got an angle labelled as 40 degrees, so the angle that the tension makes to the metal bar must be 50 degrees because the angles in a triangle add up to 180 degrees. I can then take moments about the hinge and I need to resolve the component of the tension that is perpendicular to the metal bar. Now because that will be the opposite side of the triangle, I will be using sine of that angle. So T sine 50 multiplied by 0.75 is going to be the anti-clockwise moment. The clockwise moment is being caused by the weight. The weight is calculated by doing 12 times 9.81, which is 117.7, and then I can multiply that by the distance from the pivot, which is 0.375 metres. I make those two things equal to each other because of the principle of moments, and then dividing by sine 50 times 0.75 gives a value of the tension as 76.5 newtons. Okay, on to some summary questions then. There's three sets of questions of increasing difficulty. We've got consolidation questions, standard demand, and then for those of you that are pushing for the highest possible grades, A's and B's, you'll need to have a go at the stretch and challenge questions as well. So the first question on consolidation says 1A part 1, name two scalar quantities. A bit of a recap from right at the start of the topic here. There's loads of different scalar quantities that we could name. I've given you 4 different examples that you could pick from there. You could have distance, speed, mass or energy. 1A part 2 says name two vector quantities. Again, just a simple recap from earlier on in the topic. You could have displacement, velocity, momentum or force. Okay, part B. The helicopter shown in the diagram is moving through still air. The lift force from the helicopter's blades is A, and it wants us to name the forces labelled B and C. Well, because the helicopter is moving through the air, there has to be some sort of air resistance acting on it, and that will be acting against the motion of the helicopter. So therefore, force B must be air resistance. If you look at force C, that is acting straight downwards, and so that is obviously going to be the weight. Part 2. The force vectors are shown arranged in a triangle as shown in the diagram. State and explain how the diagram shows that the helicopter is moving at a constant velocity. Well, the condition for constant velocity is that the resultant force must be 0, and we can see that the resultant force is 0 because the forces are making a closed triangle of vectors. Part 3. The lift force is 9.5 kilonewtons and acts at an angle of 74 degrees to the helicopter. We've been asked to calculate the weight of the helicopter and give our answers to an appropriate number of significant figures. Well, if we consider equilibrium in this case, then what is balancing the weight is the vertical component of that lift force. So to work out the vertical component of that lift force, I would do 9.5 kilonewtons multiplied by sine 74. I'm using sine 74, of course, because I'm working out the opposite side of that right angle triangle. So 9,500 times by sine 74 gives me an answer of 9,132 newtons. You would lose a mark for quoting that as the final answer though, because everything in the question has been quoted to 2 significant figures. 9.5 is 2 sig fig and 74 is 2 sig fig, so I would have to round 9,132 to 9,100 newtons. Standard demand questions. A uniform plank of length 5 metres rests horizontally on 2 bricks that are 0.5 metres from either end. A child of weight 200 newtons stands on one end of the plank and causes the other end to lift, so it is no longer supported at that end. Calculate the weight of the plank. As always with a moments problem like this, I would draw it out. What is worth noting in this case is that although the diagram makes it look as though this is a 2 support problem, it actually isn't. Because that child has made the other end lift, the far support is no longer in contact with the plank of wood. So when we draw it out, we only have the one pivot point. We know the weight of the child is 200 newtons and he's 0.5 metres away from the pivot point, and then the weight is acting from the centre, meaning that that is 2 metres away. It's now just a simple moments problem, so 200 multiplied by 0.5 is going to be equal to 2 times W. Simplifying that, we can do 100 divided by 2, which gives us the answer of 50 newtons. We're then asked to work out the support force acting on the plank from the supporting brick. Well, to do this, we can just consider the equilibrium of forces. The vertical forces have to balance out. So going downwards, we have 200 newtons and 50 newtons from the weight. So the force that the support is putting on the plank of wood has to be 250 newtons in the opposite direction. Question 2. A security camera is supported by a frame that is fixed to a wall and a ceiling as shown in the diagram. The support structure must be strong enough to withstand the effects of a downwards force of 1,500 newtons acting on the camera in case the camera is gripped by someone below it, obviously a criminal trying to get away with some criminal activity. We've been asked to calculate the moment that a force of 1,500 newtons on the camera about the point where the support structure is attached to the wall. Moment is obviously force multiplied by the perpendicular distance from it. We'll assume that that 1,500 newton force is acting perfectly downwards, so we just do 1,500 times by 1.2, which gives us 1,800. Of course, include the unit of Newton meters. We've been then asked to calculate the extra force of the vertical strut supporting the frame when the camera is being pulled with a downwards force of 1,500 newtons. So, to do this one then, we simply need to balance out the moments because of course that force from the support strut is going to be balancing it. Now that is only 1 metre away from the pivot point, so F times 100 has to be providing that 1,800 newton meters, so the force must be 1,800 newtons. Stretch and challenge questions. A crane is used to raise one end of a 15 kilonewton girder of length 10 metres off the ground. When the end of the girder is at rest 6 metres off the ground, the crane is perpendicular to the girder, and we've been asked to calculate the tension in the cable. Now, this is actually a moments problem. I appreciate the diagram looks a bit different to the ones that we've done already, but basically the tension in the crane cable is going to be providing an anti-clockwise moment on that girder, and the weight, which will be acting from the centre of the girder, will be providing a clockwise moment. Now I've sketched out the information that we know so far, but obviously as we can see there, the weight is not perpendicular to the girder in this instance, and we need it to be. Now we can work out what the component of the weight that is perpendicular to it is if, I'm just going to get the laser pointer, if we know what the angle that this will be here. You might remember when we've done incline problems, we've worked out what the angle that the weight is to a line that's drawn back here would be. If we know what that angle is, then we can resolve that 15,000 newtons. Now this angle that this line makes will actually be the same as the angle that the girder has been lifted. Again, you might remember that from incline problems, but what we will need to do is find a way of working that out now. So if we draw a diagram of the distances that we know the girder is 10 metres long and it is 6 metres off the ground. We can therefore work out what the angle that it's been raised up by is using the triangle as shown there. Now we know what the hypotenuse is and we know what the opposite side is. Therefore we can say that 10 sine theta is equal to 6, and so theta is sine to the minus 1 of 6 over 10, which is 36.9 degrees. It now becomes a case of saying, well, 15,000 newtons times by cos of 36.9 is going to be the component of the weight that is perpendicular to that lever. It will be providing a moment from 5 metres away from the hinge point, so the clockwise moment is going to be 59,976 newton meters. The anti-clockwise moment provided by the tension is going to be 10t, nice and simple. So we equate those and divide by 10. So the tension in the cable is going to be virtually 6,000 newton, the exact answer being 5,997.6. We now want to calculate the support force on the girder from the ground, or we want to show what it is, rather we want to show that that is 3.6 kilonewtons, and we want to show that the vertical component of the support force on the girder is 10.2 kilonewtons. Then we want to calculate the magnitude of the overall support force. Well, I've drawn here a diagram that shows all of the different situations that are going on. We have got the tension, which is 6,000 newtons virtually, as shown there. Now that tension will have a vertical and a horizontal component. I've labelled the weight, but of course the support force that is acting as well is going to have a vertical and a horizontal component. So to do this then, it is more or less, just click on, a case of just considering the equilibrium of forces. That 6,000 newtons that's caused by the tension, the vertical component of that is going to be 6,000 cos 36.9. If you want to see why that is the case, I've drawn a diagram showing the angles below there. The angle of the incline is theta, so the first thing to consider is that the Z angle will also be theta, and then because the vertical component of the tension is at 90 degrees to the top of that Z line, then obviously that will be theta as well. So the tension going upwards is 6,000 cos theta. We have to add to that the vertical component caused by the support force, and that has to equal the total force going downwards, which is 15,000 newtons. So a little bit of simple rearranging there tells us the vertical component of the support force is 10,202 newtons. We then apply similar logic to the horizontal forces. The only horizontal force in this case that we know is the horizontal component of the tension, which is going to be 6,000 sine 36.9. So that has to be equal to the horizontal component of the support force. So therefore we can say the horizontal component of the support force is 3,600 newtons. We then want to find out the magnitude of the support force overall, and we do that using Pythagoras' theorem as we've done in previous lessons. So root 10,202 squared plus 3,603 squared gives us a support force of 10,820 newtons. Question 2. A small toy of weight 2.8 newtons is suspended from a horizontal beam by means of two cords that are attached to the same point of the toy. One cord makes an angle of 60 degrees to the beam and the other makes an angle of 40 degrees to the vertical. Calculate the tension in the cord. Now the diagram that's given in the question is the one that's backgrounded in pink there, but I have redrawn this to make it clearer what forces and angles are acting. Now it doesn't matter what you call these two tensions, I've opted to call them T1 on the left and T2 on the right hand side. It doesn't matter though, as long as we're coming out with the same answers at the end for the two different values. Now, what we need to do is think, well, if we're in equilibrium, the force going up will be equal to the force going down. We have 2.8 newtons going downwards, so the forces going up will be the vertical component of T1. That will be the adjacent side, so I'm going to use cos, so T1 cos 40, and then I want the vertical component of T2, which is going to be adjacent to the 30-degree angle, so T2 cos 30, and those added together make 2.8. Now I can't solve that equation because I've got two unknowns in the same equation, which is a problem for me. So I need a second equation. I can look at equilibrium horizontally, and the horizontal component of T1 is going to be T1 sine 40, and I would have to balance with T2 sine 30. So that therefore gives me a second equation with the same two unknowns, and I can now solve this as simultaneous equations. To do this, I'm going to use the method of substitution. There are other ways of solving simultaneous equations, of course, but I'm going to divide that second equation by sine 40 to give me T1 is equal to T2 sine 30 over sine 40. I will then replace T1 in the first equation with the values T2 sine 30 over sine 40. So rewriting that first equation gives me T2 sine 30 over sine 40 multiplied by cos 40, and then the rest of the equation is the same. It is still plus T2 cos 30 equals 2.8. I'll then factorise out the value of T2 because it appears in both of those factors on the left hand side, and then I will divide by the quantity of those brackets to give me T2 equals 2.8 over 1.5, so the value of tension 2 is 1.92 newtons. It's now a dead simple case of finding the value of T1 because I know that T1 is T2 sine 30 over sine 40, so replacing T2 with 1.92 gives me 2.8 minus 1.92 over cos 30 over cos 40, which is equal to 1.48. I realise there on the board I've actually substituted it into the first equation, but it doesn't matter whether you substitute it into the first or second one, it will still come out as 1.48.